The Bohr model of the atom. Niels Bohr revolutionized concepts about the atom with his solar system model. This model of the atom required that the electrons be confined to specific allowed orbits. Using conventional physics, the energy of an orbit with a number n is given by the formula energy sub n equals -2 times pi squared times m times e to the power of 4 divided by n squared times h squared equals -2.178 times 10 to the power of -18 divided by n squared joules, where m is the mass of the electron, e is the charge on the electron, h is Planck's constant, and n is the orbit number. Later, the number n became known as the principal quantum number. In Bohr's theory, the symbol n represents the number of each orbit, starting with the one closest to the nucleus. Energy in the form of light is emitted from an atom when an electron moves from its initial orbit to an orbit with a lower value of n. Conversely, when an electron is promoted from a lower orbit to a higher numbered orbit, energy must be added. The energy difference between any two orbits is constant. The same amount of energy needed to raise an electron from one orbit to another will be released when the electron drops back to its original orbit. Line spectra result from the emission of light by atoms, which occurs when electrons in excited atoms drop from higher orbits to lower ones. The energy emitted can be determined by subtracting the energy of the lower orbit from the energy of the higher orbit using equation 1.3. When energy is added to an atom, the atom moves from a lower energy state to a higher energy state, as shown in figure 1.4b. The energy needed to excite an electron can be calculated as the difference in energy between the final and initial Bohr energy levels. Figure 1.4 illustrates the movement of electrons between Bohr energy levels. Part A represents electrons losing energy in the form of light as they drop to lower energy levels. Part B represents electrons gaining energy as they are excited from a lower energy level to a higher energy level. Another way of describing this process is through an energy level diagram, where the y-axis represents the energy of each orbit. Instead of circles, horizontal lines represent the energy levels of the orbits. Arrows are drawn to show the movement of an electron from one energy level to another. All energy level diagrams for line spectra depict electrons moving from higher orbits, energy levels, to lower orbits. The energy of each level in figure 1.5 is calculated using equation 1.3, as shown in example 1.3. The energies have a negative sign because the electron loses energy as it drops closer to the n equals 1 level. The most stable position for the electron in the atom is the first energy level, where the electron has the lowest possible amount of energy. Figure 1.5, energy level diagram for the Lyman, Balmer, and Paschen series of lines in the spectra of hydrogen. Example 1.3. Determine the energy and wavelength of light associated with an electron moving from the second to the fourth energy level in a hydrogen atom. Solution. To use equation 1.3, we need to calculate E sub n for the initial state where n equals 2, and again for the final state where n equals 4. The difference in energy is change in energy equals energy final minus energy initial. Energy sub 2 equals -2.178 times 10 to the power of -18 divided by 2 squared joules equals -5.445 times 10 to the power of -19 joules. Energy sub 4 equals -2.178 times 10 to the power of -18 divided by 4 squared joules equals -1.361 times 10 to the power of -19 joules. Change in energy equals energy sub 4 minus energy sub 2. -1.361 times 10 to the power of -19 joules minus -5.445 times 10 to the power of -19 joules equals positive 4.084 times 10 to the power of -19 joules. The positive sign indicates that energy must be added to the atom to achieve this transition. The wavelength of this energy is calculated using change in energy equals Planck's constant multiplied by the speed of light divided by wavelength. Rearrange. Wavelength equals Planck's constant multiplied by the speed of light divided by change in energy equals 6.63 times 10 to the power of -34 joule seconds multiplied by 3.00 times 10 to the power of 8 meters per second, divided by 4.084 times 10 to the power of negative 19 joules. The size of the atom. Bohr postulated that the momentum, defined as mass multiplied by velocity, of the electron must be related to the size of the electron's orbit. The relationship he used was mass multiplied by velocity equals principal quantum number multiplied by Planck's constant divided by 2 pi multiplied by radius. When Planck's constant, h, the electron mass, 10, and the electron velocity, v, are entered into the equation for the first energy level, where SAR n equals 1, a radius of 53 picometers is calculated. If n equals 2, the orbit radius is 106 picometers. The value 53 picometers is often called the Bohr radius for the hydrogen atom. The radii of the other orbits are whole number multiples of the Bohr radius. The Bohr radius provided chemists with a theoretical value for the size of a hydrogen atom and confirmed that the atomic sizes determined by experiment were indeed reasonable. The wave mechanical model of the atom. Soon after Bohr's achievement, for which he received the Nobel Prize, Louis de Broglie suggested that the electron could behave as a wave as well as a particle. One way of looking at this duality involves the equation for the energy of a wave. Energy equals Planck's constant multiplied by frequency equals Planck's constant multiplied by the speed of light divided by wavelength. And Einstein's well-known equation for the energy of a particle. Energy equals mass multiplied by the speed of light squared. Since the electron can have only one energy at any given moment, energy in both equations must be the same, resulting in the equality. Planck's constant multiplied by the speed of light divided by wavelength equals Planck's constant multiplied by frequency equals mass multiplied by the speed of light squared. This shows the obvious relationship between the particle, meaning mass, and wave, meaning frequency, nature of the electron. Since all particles do not move at the speed of light, we use the symbol velocity for the speed of the particle to get Planck's constant divided by wavelength equals mass multiplied by velocity. Describing the motion of an electron as a wave required the use of complex wave equations. Actual use of these wave equations is left for higher-level college chemistry courses. However, it is important to understand the results of using these wave equations, which can be summarized as follows. 1. The wave equations require 3 numbers, called quantum numbers, in order to reach a solution. These are the principal quantum number, azimuthal quantum number, and magnetic quantum number. In addition, to specify an electron completely and uniquely, a 4th quantum number, called the spin quantum number, is needed. There are specific rules for assigning the 4 quantum numbers to electrons, but this is not required on the AP exam. 2. The wave equations drastically change the picture of the atom, refer to figure 1.6. In particular, the fixed orbits of the Bohr theory are replaced with a cloud of electrons around the nucleus. The modern orbit is the region of space in which the probability of finding the electron is highest. Figure 1.6. Comparison of the Bohr model and the wave model of the hydrogen atom. 3. The circular orbits of the Bohr theory have been replaced with spherical electron clouds. The wave equations have shown that the shapes of most electron clouds, although more complex than Bohr's orbits, are still simple geometric shapes. Number 4. The arrangement of electrons deduced from wave equations agrees well with the periodic table. Many physical and chemical properties of elements and compounds are more fully understood with the knowledge gained about the electronic structure and orbit shape. 5. The results of the wave equations agree completely with the Bohr model. Specifically, the energy change for an electron moving from one electron cloud to another agrees with Bohr's calculations. In addition, the identical 53 picometer radius is found for the electron cloud in the wave model of the hydrogen atom. 6. The Heisenberg uncertainty principle is fundamental to the wave model of the atom. This principle states that both the position and the momentum of an electron cannot be exactly known at the same time. The more precisely the position, x, of the electron is known, the more uncertainty exists as to its momentum, mass multiplied by velocity. Heisenberg's uncertainty equation is as follows. The uncertainty in position multiplied by the uncertainty in momentum is greater than or equal to Planck's constant divided by 4 pi. Mathematically, this is expressed as change in position multiplied by change in mass times velocity is greater than or equal to Planck's constant divided by 4 pi. This equation reads, the uncertainty in the position multiplied by the uncertainty in the momentum is greater than or equal to Planck's constant divided by 4 pi. The concept of this equation is important, although no questions involving a numerical solution will be asked on the AP Chemistry exam. Structure of the atom. Principal energy levels, also known as shells. In the current model of the atom, the positively charged nucleus is surrounded by one or more principal energy levels, also called electron clouds. Principal energy levels may also be referred to as principal shells, in reference to Bohr's atomic model. In either case, the principal energy level, or principal shell nearest the nucleus is assigned the number 1, and each succeeding energy level is numbered with consecutive integers. The largest element known needs only 7 principal energy levels to hold all of its electrons. The number of the principal energy level is represented by the symbol N, which is the same as the principal quantum number discussed later. Since the principal energy levels become larger, the farther they are from the nucleus, they can hold correspondingly more electrons. Each principal energy level can hold a maximum number of electrons equal to 2 multiplied by n squared, where n is the principal energy level number. From this, we can calculate that the first 4 principal energy levels can hold 2, 8, 18, and 32 electrons, respectively. The last 3 energy levels could theoretically hold 50, 72, and 98 electrons, but they are not completely filled. Sublevels, also known as subshells. Each principal energy level within an atom contains one or more sublevels. These sublevels may also be referred to as subshells in older terminology. The number of sublevels possible in each principal energy level is equal to the value of function for that energy level. For instance, the third principal energy level, where n equals 3, may contain a maximum of 3 sublevels. For the 118 known elements, only 4 sublevels are actually used. The 5th, 6th, and 7th sublevels, corresponding to n equals 5, 6, and 7, are theoretically possible, but are not currently needed. Sublevels are numbered with consecutive whole numbers starting with 0. These numbers are called the azimuthal quantum numbers, represented by the symbol L. The value of L can never be greater than n-1. In addition to the numbering system, the sublevels are also given corresponding letters, S, P, D, and F. Table 1.2 shows the sublevels possible for each energy level. It is important to remember that a sublevel will not exist unless the atom has enough electrons to occupy at least part of the sublevel. Each principal energy level has an S sublevel. All except the first have P sublevels, and the D and F sublevels are found in more than one principal energy level. To distinguish one sublevel from another, chemists usually combine the principal energy level number with the sublevel letter to indicate in which principal energy level the sublevel is located. With this method, the designation 4p tot indicates a p sublevel in the 4th principal energy level. Table 1.2 sublevels in the atom. For principal level n equals 1, the possible sublevel numbers are 0, and the sublevel letter is S. For principal level n equals 2, the possible sublevel numbers are 0 and 1, and the sublevel letters are S and P. For principal level n equals 3, the possible sublevel numbers are 0, 1, and 2, and the sublevel letters are S, P, and D. For principal level n equals 4, the possible sublevel numbers are 0, 1, 2, and 3, and the sublevel letters are S, P, D, and F. For principal level n equals 5, the possible sublevel numbers are 0, 1, 2, and 3, and the sublevel letters are S, P, D, and F. For principal level n equals 6, the possible sublevel numbers are 0, 1, and 2, and the sublevel letters are S, P, and D. For principal level n equals 7, the possible sublevel numbers are char 0 and 1, and the sublevel letters are S and P star. Only sublevels used by the known elements are shown here. Tip: the value of n also indicates the number of sublevels within each principal energy level. Orbitals. Each sublevel of the atom may contain one or more electron orbitals. An orbital is defined as a region of space that has a high electron density, and each orbital may contain a maximum of 2 electrons. To share an orbital, 2 electrons must have opposite spins. When 2 electrons share an orbital, they are said to be paired. Orbitals are designated as s, p, d, or f, according to the sublevel they are in. Tip: each orbital can hold only 2 electrons with opposing spins. The number of orbitals that a sublevel may have depends on the azimuthal quantum number, L, of the sublevel and is equal to 2L plus 1 tine. From this fact, we see that there is 1 s orbital in an s sublevel, 3 p orbitals in a p sublevel, 5 d orbitals in a d-dront sublevel, and 7 f orbitals in an f sublevel. Table 1.3 summarizes this information. Table 1.3, Orbitals in the atom. For the 0s orbital, there is 1 orbital, and it can hold 2 electrons. For the 1p orbital, there are 3 orbitals, and they can hold 6 electrons. For the 2d orbital, there are 5 orbitals, and they can hold 10 electrons. For the 3f orbital, there are 7 orbitals, and they can hold 14 electrons. This table also shows why the principal energy levels contain 2, 8, 18, and 32 electrons, respectively. The first principal energy level has only 1 s orbital and therefore holds only 2 electrons. The second principal energy level has s and p orbitals that hold 2 and 6 electrons, respectively, or 8 for that energy level. The third principal energy level holds the sum of 2 plus 6 plus 10, or 18 electrons. The fourth principal energy level holds 2 plus 6 plus 10 plus 14, or 32 electrons. Orbitals take the same letter designation as the sublevel letter, S, P, D, or F. Each orbital is given a number, called the magnetic quantum number, m sub L. The possible values of m sub L range from negative L to positive L, including 0, as Table 1.4 shows. Table 1.4, Possible values of m sub L. For the s orbital, m sub L equals 0. For the p orbital, m sub L can be negative 1, 0, or positive 1. For the d orbital, m sub L can be negative 2, negative 1, 0, positive 1, or positive 2. For the f orbital, m sub L can be negative 3, negative 2, negative 1, 0, positive 1, positive 2, or positive 3. Tip: orbital shapes are noted as a letter or a number for the quantum number L. The designation of a sublevel also tells the chemist the shape of the orbitals within that sublevel. In s sublevels, the shape of the electron cloud is spherical. 4. The s sublevel in the first principal energy level has the highest electron density within a sphere 53 picometers from the nucleus, as Bohr predicted. In the second and higher numbered principal energy levels, the s sublevel has a high electron density at the expected distance from the nucleus, which is the principal energy level number multiplied by 53 picometers. These sublevels also show an appreciable electron density at all of the lower energy level radii. Figure 1.7 illustrates this feature of the s sublevels. The p orbitals have a dumbbell shape, with the electron density being greatest in 2 lobes on either side of the nucleus. There are 3 p orbitals in each p sublevel. Each orbital is oriented along a different axis, as shown in Figure 1.8. These orbitals are often designated as p sub x, p sub y, and p sub z. Figure 1.7 shows diagrams of the 1s, 2s, and 3s orbitals. These diagrams highlight that the highest radial density for the 2s and 3s orbitals occurs not only at the expected radius but also at intermediate levels. Tip: orbital orientation in space is specified by the magnetic quantum number, m sub L. The 5d orbitals in a d sublevel have the shapes shown in Figure 1.9. These orbitals often have subscripts indicating their general locations on the x, y, and z axes. The 7f orbitals are slightly more complex in shape than the d orbitals. A knowledge of the exact shapes is not needed at this time. Figure 1.8 shows diagrams of the 3 p orbitals aligned with the x, y, and z axes. Figure 1.9 illustrates the shapes of the 5d orbitals in the atom. 4 of these shapes are identical, while the 5th is very distinctive.